What is stochastic computing? Executive summary. Stochastic computing is an energy-efficient digital method. It represents numbers as random bitstream probabilities instead of fixed binary values. SC simplifies complex math. For example, it performs multiplication with a single AND gate. This extreme simplicity minimizes hardware size and power consumption dramatically. SC also provides inherent fault tolerance against noise. However, SC requires long bit streams for accuracy, causing slower computation times than traditional binary systems. It is therefore ideal for applications like machine learning and image processing, where noise tolerance is high and power efficiency is critical. Stochastic computing, harnessing randomness for energy-efficient computation. Stochastic computing offers a radical departure from traditional digital systems. It represents a fascinating approach to computer design. SC does not use the standard binary numbers you know, and instead, it relies upon random bit streams to encode numerical values. This unique method fundamentally changes how circuits process information. Scientists and engineers investigate SC for its potential benefits. It can reduce energy consumption dramatically. It can also shrink the physical size of computing hardware. This makes SC a vital area of research for future AI systems, representing numbers, probabilities, not bits. Traditional computers use binary notation. Every number is a fixed sequence of ones and zeros. The position of each bit holds a specific power of 2. This system gives us absolute precision in calculations. Stochastic computing works very differently. It represents a number as the probability of seeing a 1 in a stream of bits. Imagine a number like 0.75. A standard computer would use a fixed binary code for this value. A stochastic computer instead uses a long sequence of bits. In this bit stream, approximately 75% of the bits are ones. The remaining 25% are zeros. The actual position of the ones is entirely random. Therefore, the number 0.75 becomes the statistical likelihood of observing a logic high signal. The length of the bit stream determines the accuracy of the representation. Longer streams provide better precision. Generating the bit stream. You need a way to convert standard binary numbers into these stochastic bit streams. This conversion process involves two main components. These components are a pseudo-random number generator, PRNG, and a simple comparator. The PRNG continuously generates random numbers. These numbers are typically uniform across a specified range. The comparator receives two inputs. One input is the value generated by the PRNG. The second input is the actual binary number you want to represent. The comparator outputs a 1 only when the random number is less than the binary input value. Otherwise, the comparator outputs a 0. If your binary input is 0.25, the output generates a 1 about 25% of the time. This simple circuit effectively translates a stable fixed point number into a fluctuating bit stream. This stream then feeds into the rest of the stochastic circuit. Simple arithmetic. Multiplication. This representation allows for incredibly simple arithmetic operations. The ability to perform complex math using minimal hardware is SC's greatest strength. Consider standard binary multiplication. A traditional binary multiplier requires many transistors and complex logic gates. This complex circuit also consumes a lot of power. Stochastic multiplication requires only a single AND gate. An AND gate outputs a 1 only if both its inputs are 1. Let's say you multiply two stochastic numbers, A and B. A is represented by the probability P of A. B is represented by the probability P of B. The bit streams enter the AND gate simultaneously. The output probability P of out is the product of the input probabilities. P of out equals P of A times P of B. You use the basic laws of probability. If two random events are independent, the probability of both happening is the product of their individual probabilities. This means complex multiplication becomes very cheap in terms of hardware resources. Adding and averaging signals. Adding two stochastic numbers is slightly more complicated than multiplication. You cannot simply use an OR gate for addition. An OR gate output would give you PA or B. This calculation gives a value greater than 1 if P of A plus P of B is greater than 1. The output probability must remain within the range of 0 to 1. Stochastic addition involves a key concept called scaling. To add two numbers, A and B, we first use a multiplexer, MUX. A MUX selects one of its inputs based on a separate control signal. We use a control bit stream S with a probability P of S equals 0.5. The MUX selects A half the time and B the other half. The output stream's probability is the average. P of out equals P of AI plus P of B divided by 2. This operation is actually averaging, not pure addition. To achieve true addition, you must pre-scale the input values. You would scale A and B by 0.5 before the process begins. This allows for scalable and efficient addition within the probability limits. The huge advantage: size and power. One compelling benefit of stochastic computing is its incredible hardware efficiency. SC circuits use dramatically fewer logic gates than their binary counterparts. A standard binary multiplier needs hundreds of transistors. The stochastic AND gate needs only a few transistors. This size reduction means SC circuits occupy a much smaller area on a silicon chip. This characteristic is called area efficiency. The reduced gate count directly translates into major power savings. Fewer switching transistors consume less energy. This is especially true when performing thousands of simple operations every second. Modern computing, particularly AI, faces a huge energy crisis. Systems like those used by normal computing often focus on efficiency. SC provides a promising solution for energy-constrained devices. It allows complex calculations in environments where battery life or heat dissipation is critical. The strength of robustness. Stochastic computing exhibits a natural level of fault tolerance and noise immunity. Traditional binary circuits are highly sensitive to errors. If a single bit flips in a traditional number, the entire calculation can fail completely. This single error causes a catastrophic malfunction. SC systems handle individual bit errors much better. The value is represented statistically across the entire bit stream. A single one flipping to a 0 only slightly changes the overall probability. The final result remains largely correct. The system essentially averages out the noise. This inherent robustness makes SC highly reliable in noisy or unstable environments. Imagine running a computer system exposed to radiation. The SC system would likely continue working effectively. It offers a powerful resilience against physical defects in the hardware. The major drawback? Speed and latency. Stochastic computing has significant drawbacks you must consider. The primary limitation involves latency and computation time. Stochastic systems require long bit streams for accurate results. You must wait for hundreds or thousands of random bits to pass through the circuit. Only then do you obtain a good approximation of the final numerical value. This requirement makes stochastic computing much slower than traditional binary systems. Binary computers calculate with high precision in just a few clock cycles. SC systems require many clock cycles to converge on an accurate answer. The time needed for calculation is called latency. Applications requiring instant, high-precision results are not suitable for SC. SC is best used when speed can be sacrificed for hardware simplicity and power efficiency. This trade-off defines the niche where SC operates most effectively: accuracy and convergence. The concept of accuracy ties closely to the speed limitation. The precision of a stochastic calculation depends on the length of the bit stream. A short stream gives a fast but rough estimate of the answer. A very long stream provides high accuracy but takes much longer to process. The system must wait for the probability to fully converge. We use a technique called stochastic sampling. The final answer is simply the count of ones in the output stream divided by the total stream length. This simple process provides the result. However, the calculation always contains some degree of randomness. This inherent statistical noise prevents SC from achieving the absolute precision of fixed-point binary systems. You must always decide how much accuracy you need. This decision directly dictates the necessary stream length and the overall calculation time. Real-world applications. Stochastic computing currently finds use in specific targeted applications. These applications leverage its strengths while tolerating its weaknesses. Machine learning and AI acceleration represent a prime area of use. Many AI tasks, like training neural networks, can tolerate some level of noise. The hardware simplicity of SC makes it perfect for building massive parallel AI chips. Image processing is another important application. Operations like blurring or edge detection involve simple arithmetic on large datasets. Stochastic circuits perform these tasks efficiently. Control systems, where feedback loops inherently handle noise, also benefit from SC. Furthermore, the principles of SC are being integrated into hybrid systems. These systems use stochastic methods for low-precision operations. They reserve traditional binary for the high-precision tasks. Stochastic computing has found its unique place in the modern computing landscape. It offers an alternative approach to computation for the most demanding efficiency problems.